And that record, and goes record.
Yep, got it.
Does everybody have their phone today? We're gonna make a little word cloud.
Yeah, we can.
So what I'm gonna ask y'all to do is I'm in the second year, it's gonna come up. And y'all gonna text to this number. I got it, the instructions are all here. And using 3 words, only 3 words, and it's 3 separate words. What comes to your mind when you hear new? Be thinking about it. So, for example, if I ask y'all why y'all like, why cats are nice? Cute, fluffy, and adorable. That'd be some good answers. Alright? Alright, here's the instructions. So to number 37607, text this, DFIS 341. Everybody do that? Yeah, get your phones out. Everybody got your phone? That's okay, that's okay. Well, how many of you got their phone? Everybody else got the phone? How many actually be on the phone? Alright, so we got a handful, that's cool. Go ahead and do this.
Y'all are still doing it. Y'all are still doing it.
Yeah, y'all can do it too, yeah,
Get your
please.
phone.
go ahead and do it.
Y'all are still participating.
Alright, and.
Help us keep you on the video.
Exactly. Go ahead and do that. 3 words. What comes to mind? New. I'll do it too. Working for everybody? Once you text DFIS, you'll be in it, and then you can figure out, you can put in whatever answer you want. Okay. Somebody got in. We'll see something they wrote up here. Do y'all use like Wi-Fi to text, or do y'all have like messaging? Alright, this ain't working too well. This ain't working too well. Alright, so somebody, who got in protons? Who put in protons? Who was it? Sue? Come on, guys.
There's a good one, gravity. There's a good one for Newton.
Yeah, gravity.
Keep going, put in some more
This
there.
is good stuff. Science, yeah. Newton is like the father of science. Alright. And DFIS 341. Okay, we still got some stuff on there. Motion. There we go. That's a hot one. Motion.
Can I say one since I don't
Go
know?
ahead, please.
Laws.
Laws, excellent. That's great. What are we talking about? We use laws today. What the word cloud does is like the biggest words, those are like what's been sent on, and obviously that was like the keyword to get in, so, and it kind of messed up. Sorry about that, y'all. But this just shows you like what everyone's thinking. So it looks like all the other words just have one response: gravity, science, electron, motion, proton. But so we can't get too much like discussion in this, sorry, but we'll just move on. So like, we did to start our discussion on Newton, when we talk about forces, what is a force? Anyone want to take a stab at that? A force isn't something that pushes. Excellent. That's half the definition, clearly. Anything else? What's up?
Basically, forces object weight.
Okay. Yeah, so two objects in some kind of relationship with each other, something's happening between them. Is that what you mean? Okay, that's excellent. So this is how we're going, in this class, this is how we're going to think about the force. A push or pull that may cause an object's motion to change. So, like, things like love, is that a force? Dr. King, you want to comment on that? Is love a force? Yes? You got a yes? They get you thinking, yeah. Because like, ooh, love, man, that like pulls people together, bond, it bonds them. But we're gonna think about, in this class, force, it's a more physical thing. The unit, for y'all know all about units by now, the unit is the Newton. And anybody know how much a Newton is? It's actually just a pretty small amount of force, 1 Newton. So if you ever, anybody bench press, anybody lift weights? So if you bench press 100 pounds, that takes about 450 newtons of force, all right? So 1 Newton is actually, it takes you about 4 newtons of force to lift something that's about 1 pound, all right? And it's a vector quantity. That means we're going to be talking about it mainly on tests. You'll see that it's written in like arrows. Now we'll show you some examples later. And it's all about the direction that it's going, all right? So this is what I'm talking about.
Excuse me.
What's up?
Can you go back just for?
Sure, no problem.
Sorry,
That's okay.
just for the Newton part. All right. Okay.
All right. Forces are measured in newtons. So the forces have to be in contact with each other.
No.
Think about this. Nope, here nose. Nose. So, but can they be in contact with each
Yeah.
other? Anybody got an example of that? Think what's up?
Like a car accident?
Exactly, that's an excellent example. There's lots of force in collision in a car crash. So, you have a question? Magnets, there you go, right there, we got the, what kind of force is that?
Magnetic.
Magnetic, bam, right there. And there's no like physical thing. And magnetism, that's actually a wave. How much you know about waves by now? We talked about like orbitals and we'll talk about waves. Waves are a key point of Newton's ideas. Oh, sure, I didn't know I did that. That's cool. All right, damn. All right. Before we do that, what do you think a balanced force is? What's something that's balanced? Balanced force is two forces.
Is it sort of like a force that equals each other out? Like a car accident, one car, if you have 2 Hondas that are like the same car,
Yeah.
instead of a truck and a Honda going, it's like the same equal amount?
Yeah, you hit the nail on the head. That's perfect. Balanced force. Check it out. Forces that are equal in magnitude, but they are opposite in direction, so they oppose each other in their direction. So left, right, up, down, whatever direction it may be. All right? And then you got unbalanced forces, which most forces you'll find are probably unbalanced. So they are not equal in strength, and they may oppose each other. So we got 2 factors. We got strength and we got direction. All right? That's what determines if it's balanced or unbalanced. Strength and direction. The graphic is a good example here. Like, see in a tug of war, if you're even, you're pulling and there's no movement, you're balanced. On each side, there's just as much pull on the other side as there is on your side. So then you're going to have no movement. We're not causing change in motion. But unbalanced forces, they'll always cause a change in motion because, and another key point is, that's not really in like the lecture, is you can think about these things in terms of energy. The energy here, it's even. And over here, you got the rocket lifting off, the jet propulsion that lifts it up off the ground. That movement is an unbalanced force because you can see the motion. You can see the rocket lifting up. Everybody got this? Do you need to know more? You can just focus on key points, notes if you want. Everybody got it? You good? Alright, go on. So, some quick practice. We got 50 in on the left, 50 in on the right. Balanced or unbalanced? Perfect. Balanced. Alright, this next one, super easy. 50 in on the left, 150 on the right, what we got? Bam. Just like that. Y'all see right here, 50 in on the left, if they're not equal to each other, it's unbalanced. Now what about this one? 140 in up top, 140 in down low. Balanced, imbalanced? Excellent. Excellent. These ends, like, and you might have got tripped up because, oh, maybe like, what if gravity's in there, you know, this acting. These arrows, these will tell you, and you see these on your exams and stuff, they represent the total net force, the total force that way. So remember that. That's total, unless it's other like explicitly stated. Because if you were thinking about, ooh, maybe like gravity's adding it down, that's a good way to think. But these arrows will represent the whole force, right? Alright. A little bit more practice. What's this? Bam, unbalanced. 7-11. What about this one? Balanced. Perfect. Y'all got this. It's easy. Probably boring, it's easy. Alright, net force. This is just a little bit different. This is just you're adding it up. If you got your positive force like pushing away, and if you got an opposing force that's going to subtract the overall energy of the system. So yeah. If there's no net force, you're not going to have any movement. But if there is a net force, however much, you will have movement. This is real simple, guys. Y'all probably get this, no problem. Just like basic math. What's the net force down here? What you think? 20 in going that way, negative 20 going that way. What's your net? What's the total? Think about it. Positive 20? Negative 20? 0. Bam. I got it. Super simple. 0 newtons. Then we got there 18 positive. Negative 20. Alright. What's the net force here? First, is it balanced or unbalanced? Unbalanced? Balanced? What is it? Unbalanced. Got it. Bam. What's the net force? 30. What way? Left. Left. You got it. Perfect. You already got this math too. Net force, what is it? Balanced. Balanced? And what's the total net force?
0.
0. Perfect. Y'all blowing through this. We're going to get down there today. Y'all have some time off again. Alright, what's net force here?
Unbalanced.
Unbalanced? What way?
Right.
Right? How How much? How many newtons?
10.
Alright, what about this one? Quick practice. Unbalanced, what way is it going?
Now,
Down, how many newtons? How much? 130, perfect. See, y'all got into the garden. This is like, y'all beyond this. Alright, what about this one? Unbalanced, perfect. How many newtons?
360 to the right.
360 to the right. Masterful. Alright, Newton's law. We got, does anybody know Newton's first law? Just off of memory.
Is a motion that it stays in motion, an object in motion stays in motion unless a force is put upon it. Or put at rest, something like that.
Okay, you got the basic gist of it. Everybody heard that before? Inertia. That's what they call this. I call it like Newton's inertial law. Because like inertial, the first one, it's like, check it out. That's how we're going to formally define it. The tendency of an object to not, to resist change in motion. Alright? What? So why does this happen? Why do objects resist change in motion? Like, there are two important factors we're looking at here. So like, is it easier to push over the skinny college boy or fully grown Mr. Newsom? Skinny college boy, why? Smaller, so what's that?
Less mass.
Mass, man, perfect. Y'all got this, no problem. So mass, that's the first most point. Now, like, say someone was trying to push me over, is it easier to just, go, bam, staying still? Or how about, like, if I get a big old run up and go, like that? Which is easier? So what about what I did made it easier to move me? So what's that? Motion, perfect. Man, y'all love this, I swear. Alright. So what's it depend on? Motion and mass. I just got it. See, like in this example, you got the guy, you're going uphill, moving it, that's a big mass. Alright. Everybody done this though? Exactly. An object stays at rest. Remember this now. Remember this. This is one key importance. In the inertial law, initial one, an object stays at rest, and an object in motion stays in motion unless acted upon by an unbalanced force. Alright. This is going to frame our discussion for later, right? And I think y'all really going to be interested in what we're going to talk about later. This is the easy stuff. This is just knowledge. Not too cognitively heavy. All right. Everybody remember on this? You got it? All right, cool. All right. You already got this. Mass and motion. That's what gives an object inertia. So like in my example, I'm small and Mr. Newton's fully grown, so it's easier to push. It's easier to move me because I'm less massive. All right. Does anything else affect inertia?
Gravity.
Gravity, that usually always affects it on Earth and everything we do. So, excellent, good point. So, anything else anybody can think of?
Friction.
Friction? Wow, y'all on the ball. All right. Everybody ride a bike? We've seen everybody over there. We all ride a bike. So, why is riding a bike easy? Once you get going, it's really easy, right? And the bike just keeps itself upright, Does anybody know what's going on there? Like, any thoughts on that? Any comments? Some type of balanced force. Good, good. Like the way you're thinking. I'm gonna show you a little video. The thing that actually caused this, I don't even understand it fully, but it's this thing called angular momentum. So check this out.
This is a gyroscope. It consists of a metal wheel mounted on an axle.
You don't have to take that
The
out.
wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel. The first thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel is creating a force that holds the gyroscope upright. When the wheel stops, the force disappears and the gyroscope falls. Incredibly, this force will support the gyroscope like this. It appears to be levitating.
Look at that, it's crazy.
A spinning gyroscope will balance on a string. You can even lift the gyroscope with a string looped around one end. This interesting behavior is difficult to explain. Physicists have determined that a rotating wheel has angular momentum, similar to the momentum that a stone flying through the air has. To change the direction of the stone requires a force. Similarly, changing the orientation of the rotating wheel requires force. The spinning wheel prefers to stay oriented as it is, and it resists any attempt to change that orientation. The fact that gyroscopes will maintain a particular orientation in space is very useful. In modern aircraft, an inertial guidance system uses spinning gyroscopes to monitor and control the orientation of the aircraft. The gyroscope is suspended in a special cage that allows it to maintain its orientation independent of the aircraft's position. If the aircraft rolls, electric sensors and contacts connected to the gyro send information to the pilot about the aircraft's orientation. The Mars rover explores the surface of Mars using spinning gyroscopes to provide stability and navigational information. This full-size robotic helicopter flies without an onboard pilot. Gyroscopes provide stability and navigation. Gyroscopes have become essential components of aircraft, ships, robots, and spacecraft. If you're interested in experimenting with a gyroscope, they are available from online science and hobby retailers. The gyroscopes I'm using are manufactured by Tedco Manufacturing in Hagerstown, Indiana. They are identical to toy gyroscopes first manufactured over 90 years ago. More science and technology related videos can be found at our website, hylaroad.com.
Alright, so that's pretty cool, right? That's some of the applications of the stuff we're talking about here. And it all started with Newton and his laws. And we've been able to apply it to things like that. In our planes, spaceships, whatever. And that's what a lot of scientists do. They just make applications like that and make it happen. So, we'll skip this slide. Alright. So, And angular momentum, now that's a, do you want to comment on angular momentum? Dr. Yusuf? Guys, I don't know that much about it, but it's just a crazy force. Like, it's with riding a bike, it's with things like this. Like if I try to bounce the ball on my finger like that, it's really hard, alright? So, I gotta really struggle. But then, you know, you do the thing, and it's just ridiculously easy. It's just like that. So, and that's angular momentum. And it's a conserved force. And it's with things with like orbitals, like the planets rotating around each other, and like Earth going around the sun. That's all angular momentum. It's a really crazy force that's just present everywhere. So, and then we had friction mentioned already. How come my old ball looks like this? I had to get a new ball just a little while ago. Why is it all messed up? Exactly. It's all that friction that creates wear and tear on the ball. It's kind of like weathering. You might have heard in environmental science. It's just like, and when you get real small at the molecular level, you have all kinds of molecules interacting with each other, and it causes friction and breakdown. So, and it creates heat, so energy. And you can think about all these things in terms of energy. And like in this example down here, we're gonna pretend that's Coke. We know it's not Coke.
Root beer.
Why does it? What's slowing this Coke down as it slides across the bar? Perfect. Y'all got it. Friction of the bottom of the cup against the top of the table. Even if that's a smooth surface, there's still friction. And you got things like Teflon. You know those pans you can make and like your egg just slides off it. That's like minimal friction. That's like they engineer that, the very molecular structure of that, so that it has as little friction as possible. So the molecules interact with each other as little as possible. Alright, Newton's second law of motion. This one is really, really easy. It's called the law of acceleration, and all it is a formula. Really simple. I think here it is right here. F equals ma. Force equals mass times acceleration. And this is just like every other formula y'all learned. You can switch around the parts. If you want to find mass, you just divide by acceleration on both sides, and then you got m equals f over a. Y'all know this.
What's our way of changing that around? Simple circle. So go ahead and draw your simple circle. You should be able to do that.
Remember this one. This was important.
So F goes on top? Or it's on the back?
I call this Newton's second fan. Newton's second fan. Because you could like, F equals A times M is the same thing. So you'd be like Newton's second law, Newton's second fan. The inertial law, and Newton's second fan. We good on this? A little bit of practice. Alright. So we got a force. Now we got a mass and we got acceleration. What's our force? Anybody want to walk me through this? F equals ma. Okay, there we go. 500 times 1, so we got F equals mass times acceleration. So this is just a straight up formula. Multiply these two together. What we got? 2,250. This is super simple. Y'all got this. One more. You got to change around the formula here because you got mass, mass and force. So we're going to solve for acceleration. So divide by m. If we get acceleration equals force over mass. Bam. Bam. Y'all know how to do this. We good on this? We good. Alright, cool. Alright, another example here. So now we got force and acceleration. So we need mass. So we're going to switch around the formula. What do we do? Divide by A. Everybody see that? Bam. divided by A, F over A, mass equals F over A. And then 140 over 3. What, anybody do that in their head? What's 140 over 3? That's like, trying to do that in your head. Practice do that in your head, though. It's like simple math. Because I was really gonna do that in life. You just do this math real quick. That's like 40 something. 40, yeah, 46.7. Yes. Alright. I think y'all good on this. Alright. We good. So Newton's third law, super simple. We're almost done. This is the last thing y'all gotta know for today. Then we good. For every action, there's an equal but also an opposite reaction. So, you know, if I punch my board up here, I'm mad. Don't take the frustration on inanimate objects. Don't do that. That doesn't help much. I take that an equal amount of I've transferred force into the wall, but also force the wall transfers force into me. All right. Energy is always conserved in the system. It's always maintained. Energy is never destroyed. Maybe in a black hole. We don't know. I don't know about that. We're still working on that. Think of these things in pairs. We're talking about balanced and unbalanced forces. We got two forces. Are they balanced? Are they unbalanced? How many newtons? What's the net force? What are we looking at? Think about these things. All right, everybody good here? I think of this as Newton's third action. For every action, there's an equal and opposite reaction. Good enough. All right, we're almost done, guys. We're almost done. And then we're going to talk about something really interesting in your life. All right. And you're going to have to help me with this one, because I couldn't even figure this one out. All right, so which of the following scenarios does not represent Newton's third law? A rocket being launched in space, a book resting on a desk, a person propelling a canoe, or a large force pushing on a small mass, causing it to decelerate. What do y'all think? I think we thinking A. What else? Anything else?
I think C.
Think C. So we got A and C. Anybody think it's B? That sounds interesting. So that's probably balanced. That's probably that would make sense. That would represent Newton's third law. For every action is equal and opposite reaction. I was thinking B actually. I was thinking B, but I'm not sure. What's the answer to this one?
Answer's D.
The answer is D.
Look at it. So Newton's third law says that there's, for every action, there's an equal and opposite reaction. A rocket being launched into space. So you've got to think about it like action-reaction forces. So a rocket being launched into space, what's the action force? What has to happen before the rocket can go into space?
The little fire
The
thing.
fire has to go which direction?
Up.
Down. Right? The fire has to go down, so the rocket goes up. That's equal and opposite reaction, right? That's it. All right, look at a book resting on the desk. If it's just sitting on your desk, resting on your desk, there's a force pulling that book which direction?
Down.
Down, gravity, right? And then there's got to be a force doing what? Pushing it up, which would be the force of the desk, right? Because if not, the book would fall to the ground, right? If you put something too heavy on your desk, if you stack your desk full of books, and you keep stacking it full of books till it's too heavy to your desk to support it, then what's gravity going to do?
Gonna break it.
It's going to break the desk, right? So equal and opposite reaction. Now I don't know how many of you paddled a canoe before, but if you've ever paddled a canoe and been in a canoe and paddled a canoe, you know that what do when I paddle the canoe? I'm pulling the canoe paddle, right?
Yeah.
So I'm pulling the canoe paddle
Back.
backwards, but which direction is my canoe going?
Forward.
Forward, right? So that's equal and opposite reaction. The only one there that doesn't have to do with equal and opposite reaction is the last one that says a large force pushing on a small mass causing it to accelerate. Now, that has to do with one of Newton's laws of motion. Which one? Which law of motion dealt with force, mass, and acceleration?
A.
The second law, right? Which said force is equal to mass times acceleration, right? So D is the only one there that's not the third law.
I actually do think, like, because they're all related. All the Newton's laws are related. I think that one's, like D's kind of the same thing as C. It's just something, a force acting out that pushes on. I think I get the point that you're going for. Like that's straight up talking about Newton's second law, but it still does use,
Yeah,
it still does use Newton's third law, because you haven't, and you're not changing, you're not losing energy while doing this. It's maintained, because you're pushing, you're pushing me over, whatever, because I'm small, and then that causes me to fly back. That's still an equal and opposite reaction. Is that clear? Is that right?
that's
Do you
really,
agree?
anytime you have motion or no motion, you have all three of Newton's
Yeah.
laws taking place.
So
So,
this is a trick question. It's not really like any definite answer, but you get the point of this. All right. Now, I'm gonna show you this. I'm gonna show you all an experiment, and this is way above what you guys are required to know. So don't worry if you get a little bit lost. And no one, the top physicists ever, have not fully explained why this happens and what's going on here. But I believe if you really pay attention to this experiment, it might change your life. Like this tells you something about us and our universe, and it's really special. This is powerful stuff. So check this out. It's called the double slit experiment. And excuse the little animated dude. I know we now have middle school here, but this is like the best representation of the experiment. This is a real experiment. We can do this right now in this classroom if we had the correct materials, but this is just a better representation of it. It does it real quick right in front of you. So check this out.
And here we are, granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit.
Does that make sense? Basically, I got like a paintball gun, and there's like a hole in the wall, and I got my paintball gun here. I'm firing at the hole, and it's gonna make that pattern on the black wall, on the back of the wall. It's just gonna go through the holes, splat, right? That making sense? Y'all with me? All right. This is the easy part. It gets a little bit more complicated, but stay with it. I think you guys got this.
Now, if we add a second slit, we would expect to see a second band duplicated to the right.
Same thing.
Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit.
Now, does that make sense? Now, that's how waves just travel. You can, and like here, this is where the biggest wave hits, the white line. All right, does this make sense? Any questions?
we'll talk about this later. This is called diffraction right here. We'll talk about this.
All right. So, and basically, if any wave at all, like you just, like I just take my basketball, throw it in some water, or it could even be a sound wave. But in here, we're using water because it's a good visual demonstration. It would hit the slit, and then it would radiate out just like this. And the biggest part of the wave would be right here in the middle, and it would travel down here. And think of this as just some wall that measures the intensity of, or the size of the wave, the energy in the wave. Is this making sense? Does this all come together here? Real quickly. Now, we're going to add another slit, and we're going to have two of these waves propagating out.
The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
So basically, anybody want to explain? Can anybody explain this? Well, why does it make that pattern? It's a little bit harder to wrap your head around this because waves aren't actually physical matter, and they just go through space. All right. Anybody comment on this?
No, the darkest line, is that where it hits the hardest and other
Okay,
places just where
It's
it's
the opposite. It's the opposite. These white lines, this is where the big waves end up actually hitting this wall. And this black, there's actually no wave that hits that at all. Because the bottom of one wave and the top of another actually come together right there. And there's no energy that actually makes it to the wall, all right? Does that make sense? Because you had two slits and you got two different waves. Just, it makes that pattern. Two slits and a wave going through it. Just remember that. Sorry, am I annoying y'all to keep stopping and explaining? All right.
So, when we throw things, that is, matter,
This is where it gets
through
super.
two slits, we get this. Two bands of hits. And with
Exactly.
waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decided to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves
This
as a
doesn't have to make
particle,
sense. It doesn't.
becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither.
It's like do the second
And it
one.
goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to
Don't make sense.
and see which slit actually goes through.
So now we put the camera,
They put a measurement
Right in the
device by
slit.
one slit.
we're gonna watch
See
the
which one
photon,
went through
the little
and
particle,
let it
the
fly.
little particle go through it as it
But the
happens.
quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Did anybody get all that? Did anybody get, what is the significance of what we just saw?
Quantum mechanics existed because of this experiment.
So, So when we shot a little bit of matter, or a little bit of these little particles, just like think of marbles, could be a basketball, through that slit, it made this pattern. But No, see, it makes the pattern that's like long and like this. It makes that mini pattern one. When we're not looking at it, we don't have a camera right there, and we're not directly observing it, it makes this pattern looking like this. But then, when we look at it, it's like a little eyelash. When we look at it, it makes that pattern. What does this mean?
Can it be like a sense of deceiving?
What you mean by that?
Like, it's like it's sort of like something we're talking about in my social studies class, like an assumption of something that you see and taking it to what it really is. So we were assuming that it made that pattern from a distance, but if you make it close up, really it's making it so it's like your eyes can deceive you all the time. So it's really say if he's standing all the way from over here and the action is going on, you're gonna get that, but if you're up close to it, you're seeing the actual image or what's actually going on.
That's a good point, but you gotta remember they got like a little sheet that's just recording where the photons actually hit it back there, and that's always at the same distance from where you look at it. So I don't think it's like a deceit, but that's a good point, because it's important to see where you're actually observing this experiment from. Did it make sense what we did, or? I know including like the electron, shooting a little electron at it, that's kind of hard to wrap your head around. But the significance of this is absolutely crazy. We do not know what this means. The fundamental physics, the laws of the universe behave differently just because we looked at it, just because we tried to observe it. We tried to find out what was actually happening. That's like something where the universe knows we're watching, or we're trying to figure this stuff out. That's kind of scary, right?
But my question is, were the electrons like ever splitting? Were they ever splitting at one point? And if they were, when at one point, because in the video it showed them splitting apart, when at one point did they combine back together? What made them come back together?
We were trying, that's the thing we were trying to look for. That's exactly what we were trying to find out. But then, because that's the only way it can make this pattern. If it was splitting and interacting with itself and then shooting off and hitting over here in this line, another one hits over here, then after a while you've got these lines. We couldn't figure, we can't know. We cannot know that, because when we look at it, it just does this, like normal matter, like just shoot a little paintball through the slit.
I think it's an energy change.
Think it's an energy change?
Yeah.
Can you elaborate on that? What?
Like atmosphere type of thing.
Yeah.
It's just like a kid. A kid will act different around its atmospheric energy.
That's kind of what's going on here.
So it's like, if we're far away and we're acting like, or we're not paying attention, it doesn't have a sense of energy, but energy changes when something comes around. So I'm guessing it's like a sense of energy around it makes it act different.
But how does it know to act differently? How does the little photon, the electron, know we're watching it? How does it act differently? What is that about? I'm gonna leave that up to you to think about. What does that mean? It seems like, to me, it just seems like, man, there's something special about being human and having a conscience and looking for the answers to questions, to mysteries like this. Because we have the power. Man, respect yourself. Because it's looking like the universe respects us enough to fundamentally behave differently, just if we're paying attention, if we're looking at things. This is like the manifestation of attitude, something like that. You know, when Mr. Newsom, he showed y'all the study where the positive mindset, where you're more healthy if you have a positive mindset. It promotes your well-being, good health, your mental health. It's I think it's all related, I think. But what's important is what you think this means. How could the photon make a different pattern just based on if we're watching it or not? How does it know to do that? How could it do that? It's anybody want to comment? Any questions? mind blown. This is the ultimate mind blowing like physics thing, and and you never come across this in your normal line of study. You won't have to. You don't have to know this. I think this is like one of the most important experiments that humans have ever done, because what does this mean? We don't know. But you guys might figure it out. You know, you guys are the young, bright minds tomorrow. You know, like pay attention to things. Do as many things deliberately as you can, because when we do things like this, we have real effects, and we have real. This is real. This ain't a joke. You know.
But then have you ever thought then, if this is one thing that is different, then how do we know any other thing that we've studied so far just didn't change when we were watching?
Excellent question. Man, that's kind of at the heart of all this. You know, we can't really prove anything we observe or see or do, you know? And that's kind of one of the conundrums of just, you know, trying to figure all this stuff out. We don't know. We don't have the answers, but we try to get the evidence. That's all we got to work with is the evidence. And we'll keep knocking on these doors and trying to find out the answers, but maybe we're not meant to find out. And maybe something doesn't want us to find out, but that's not gonna stop us. You know, we're gonna keep. My point is, be motivated. Like, there's something special about having a conscience, being sentient, being intelligent beings that we are. We can do things no other animal is capable of doing this. You know? And I know it's weird. Like, I'm a biologist. Like, that's my passion. So I'm all about life. And this is where physics and life totally just mesh together and combine, because physics change based upon us looking at it, or it acts differently. It doesn't change. It always does this. That's what physics is always the same, apparently. But yeah, man, that's all I got for y'all.
Should we clap?
You don't have to. It's whatever you want to do.
You did a good job today.
Well, thanks. I know it was kind of